So in this second video, I will now introduce to you Bayes' theorem at a general level. What Bayes' theorem tells us is that if we have two sentences, here phi and psi, and again, the reason why I'm using these complicated Greek symbols is because the sentences can be of any complexity. So they're not necessarily simple atomic sentences, but they can also be conjunctions, say. So this theorem applies regardless of how complex the sentences are. And what it says is that if we have two sentences, phi and psi, so as long as they have non-zero probability, then we can calculate the conditional probability of phi on psi by considering the probability of phi times the probability of psi given phi over the probability of psi. So why is this a theorem, or why is this a legitimate rule of probability? Well, here I'll just show you quickly how it follows from a couple of the rules we have already seen. So last week I introduced to you the definition of conditional probability. I introduced to you what it means to talk about the probability of phi conditional on the probability, or conditional on psi. So how likely is phi given that psi is true? And the definition of that conditional probability was simply the ratio of the probability of phi and psi over the probability of psi. So the first step in our proof of this theorem, the first step in seeing why this theorem holds, that is we first understand that by the simple definition of conditional probability, we have that the probability of phi given psi equals the probability of phi and psi over the probability of psi. Then this second and final step to understanding why this rule holds is we simply apply to the numerator that is generated from applying the definition of conditional probability. We apply to the numerator of that the general rule for multiplication. And the general rule for multiplication, which was introduced on Monday, is that the probability of a conjunction is this phi and psi is the same as the unconditional probability of phi, one of its conjuncts, times the conditional probability of the other conjunct, psi, on the first conjunct, phi. So these two rules we've seen already, and by putting these two rules together, we can determine this way of understanding the conditional probability of phi given psi. So why is this theorem so important? Why does it have this name, Bayes' theorem, and why does it matter? So one reason why Bayes' theorem is so important is that it summarizes neatly in a single equation the scientific method. So suppose that H, the thing that we're wondering about its conditional probability, suppose that H is a hypothesis or a theory. And suppose that E, the thing that we're conditioning on, is a piece of evidence or an observation. So what we're asking is, what is the probability of this hypothesis or this theory given a piece of evidence which we have? That is, how much does this evidence confirm or make probable some theory which we're interested in? And what this equation tells us is how exactly the evidence can go about making a theory more or less probable. And what it tells us with this fraction is that the probabilities on the top, the higher they are, the more that the evidence makes the hypothesis probable. So that is to say, looking at the first term, the probability of H, the more probable the hypothesis already is, that will make it more and more probable given more evidence. So that is to say that if we already believe something very strongly, then we'll continue to keep on believing it, likely, given new evidence. But in addition to what's called the prior probability or the unconditional probability of our hypothesis, we also have to think about how well that hypothesis explains the evidence in question. So no matter how likely that hypothesis is in itself, if the hypothesis doesn't do a good job of explaining the evidence, if the evidence, that is to say that if the evidence is not very likely given the hypothesis, then the probability of the hypothesis given the evidence won't be very high. So, and the flip side of that is the more likely that the hypothesis makes the evidence, that is, the better that the hypothesis explains the evidence, the higher that probability is, the more that the evidence confirms the hypothesis. But then finally, we have to look at the bottom where we're talking about the probability of E, which is the prior or unconditional probability of the evidence. And having it as the denominator of the equation tells us that actually the more likely that the evidence is in of itself, the less it confirms the given hypothesis. Or the flip side of that is that the more surprising the evidence is, or that is to say, the less likely that the evidence is in of itself, that actually makes that evidence better support some hypothesis. So for instance, one aspect of Einstein's theory of relativity is that it made a very, very precise prediction about the way in which light is bent or deflected when passing by the sun. So now I'm obviously not going to go into the details of this example, but what I'm pointing out is that there was a case in which the theory or the hypothesis of relativity theory entailed an extremely precise prediction about the way in which light interacts with its surroundings. And this prediction was noticed and brought out of relativity theory before it was confirmed exactly how light worked in that way. And then later there was an experiment which showed, or an observation which showed that light in fact did work in that extremely precise way. And so if we think of the results of that experiment as evidence, it's actually extremely unlikely in of itself, or in terms of its prior probability, that the universe would turn out to be such a way that light works in this very, very particular way that the theory predicts. So it was an extremely surprising piece of evidence. And what that means is that the prior probability of that evidence was very low. And thus what that means is that because this theory made a prediction in something that was very, very surprising or very, very in of itself unlikely, that means that this number here was very low. And because this is the denominator of the fraction, it means that the overall value of the right-hand side of basis theorem is very high, which means that this evidence, the discovery that this very precise prediction was in fact true, made the hypothesis or the theory very, very likely for that reason. And that is one way in which this formula is demonstrating aspects of how the scientific method works. Now, I'll give one more example, which is one argument or piece of evidence people make against creationism is that they point out that there are dinosaur bones in the ground. And these dinosaur bones must have been from a time way longer than simply 6,000 or 7,000 years ago, where 6,000 or 7,000 years is how old that most creationists or many creationists think that the world is. But then there's one way of responding to that problem for creationism, the problem that there are seem to be very old dinosaur bones. And that response is that, in fact, Jesus or God or someone else a long time ago, in fact, put these bones in the ground as a way of testing our faith. So let's consider this hypothesis, the hypothesis of creationism, in addition to the hypothesis that Jesus put the dinosaur bones into the ground in order to test our faith, so that is the hypothesis or the theory in question. And now we wonder about it, given this evidence, which is supposed to be a problem for creationism, the evidence that there are dinosaur bones, so that is E in this case. Now, the way that this hypothesis is set up, that these bones are put in the ground as a kind of trick or test, that means that this number here is actually very high. This hypothesis, in fact, makes the evidence that there are bones extremely likely, because the hypothesis says that the bones were put in the ground. So the evidence that we have found bones, that this evidence is true, given this hypothesis that bones are put in the ground as a test, is basically 1. It's as high as possible. Okay, so that means that this hypothesis here, the kind of creationism hypothesis in question, actually makes the evidence very, very likely. And because this number is, in this case, is very high, that means that correspondingly, this hypothesis, given this evidence, should also be very high. However, what we have to look at, in addition to the probability of the evidence given the hypothesis, Bayes' theorem tells us we have to look at, in addition to that, we also have to look at the unconditional probability of the hypothesis. So it might be, for instance, that the unconditional probability of the hypothesis of creationism, as well as the idea that bones were put into the ground as a test, that might be very, very low. So apart from this evidence, it might be actually very, very unlikely that that hypothesis is true. And so if this number is very low, that will bring down the overall way in which the evidence makes the hypothesis likely. And additionally, we have to go back to this idea of the evidence being surprising or not. So we have known for actually a long time that there are dinosaur bones in the ground. And in fact, this kind of version of creationism that is under consideration, that these bones were put into the ground as a test, takes for granted that we already know this evidence. So this hypothesis actually has been created post hoc, as they say, in order to explain evidence that we already have. And because that's our evidence that we already have, the unconditional probability of evidence is very high. It's not surprising. So because in this case, this will probably be very, very high, that will mean that the overall fraction's value will accordingly be lower, which will mean that even though this kind of sophisticated version of creationism does make this evidence very likely, there's still these other factors that will bring down, that might bring down the how much, the degree to which the evidence in fact does make this hypothesis likely. So in addition to helping us understand the scientific method, which is not a topic which we will be going into in any more detail in this class, except briefly next week, I think. In addition, what's maybe more important is that this Bayes' theorem can help us understand how we should respond rationally to evidence which we gain in our everyday lives. And in fact, the majority of the questions which you'll have to solve using Bayes' theorem won't really be scientific questions, but they'll be more about how we can revise our beliefs in light of probabilistic evidence. And what Bayes' theorem gives us is a rule for any belief you might have, how to think about its conditional probability on some evidence or some new belief by calculating this fraction here. So finally, before moving on to another application of Bayes' theorem, what we have to do is I have to give you a longer version of Bayes' theorem. And this longer version is the one which you will be applying in most of the questions that involve Bayes' theorem. So in the example we worked through in the beginning of this lecture, we had to actually unpack the denominator of Bayes' theorem using the law of total probability because we weren't given this value in the question. And similarly, there'll be many questions in which we're not given directly the unconditional probability of psi. So that means that we have to apply Bayes' theorem, we have to take another step in unpacking the denominator. And so what we do is we simply unpack the denominator using the law of total probability, which should be familiar from the last lecture on Monday. So here again, I just show how we can prove this more general theorem where we unpack the denominator further. So these two steps are from above, where we prove the short version of Bayes' theorem. And then in general, we can apply this law of total probability to the denominator to get our longer Bayes' theorem. And here, this longer one, there'll be many cases in which you're given in the question, in the way the question is given, all of these probabilities will be very easy to figure out. And then you simply plug in all of these probabilities on the right-hand side and then do some arithmetic. So in the next video and final video of this lecture, I will discuss how to apply this theorem to another example.